All right, welcome back everybody. In this video we are going to talk about information related to section 5.4 of AP Calculus, using the first derivative test to determine relative or local extrema. We're going to begin by introducing you to the first derivative test and what it says, and some pictorial examples related to it so that we have a pretty good understanding of it. And then we're going to go through a couple of examples of utilizing the first derivative test. So, following test applies to a continuous function f of x. So we need our function f of x to be continuous. Okay, and the first page here we're going to look at the three situations that can occur at a critical point C. So if we find a critical point using our derivative, these are the three scenarios that can occur. The first scenario, and my graph on the left is when f prime of c is 0 as the critical point, and my graph on the right here is when f prime of c is undefined at the critical point. You notice that we see that we've got a cusp over here in this graph. So it says, at a critical point, if f prime changes sign from positive to negative at c, then the function has a local maximum value there. And we see that in this graph. F prime is greater than 0, the function is increasing, hits the critical point, and then to the right of the critical point, the function is decreasing because the derivative is less than 0. Same thing over here. And both of those scenarios produce a local maximum. When the derivative is positive and therefore the function increasing, we hit a critical point, and then the derivative is decreasing. Second scenario. Again, on the left we have where our critical point is a time where the derivative is 0, and on the right we have a time where the derivative is undefined as our critical point. But here we go. If f prime changes sign from negative to positive, then we've got a local minimum. So f prime is negative here, and therefore the function's decreasing. And then we hit the critical point, and then f prime is positive to the right of there. That is indicative of a local minimum. Same thing when we've got the cusp point down here. The function is decreasing, hits the critical point, and then the function is increasing. That again is indicative that we've got a point here where we've got a local minimum. And then the third possible scenario is when f prime doesn't change sign at c, the value where the critical point occurs, in which case there's no extreme value. And on the left here we have the derivative being positive to both the left and right of the function, or pardon me, to the left and right of the critical point. And on the right hand side here we have the derivative being negative on both sides of the critical point. And we see what happens there. There's no extreme value when there is no sign change in the derivative. And so the important thing that we're looking for in the first derivative test is we're looking for sign change in the derivative. Sign change in the derivative. Okay, over to the next page. Now we have special situations that occur when we have a left endpoint and a right endpoint. At a left endpoint, which we see in both of these pictures, I've drawn this as the left endpoint of a function. If the derivative is negative to the right of the left endpoint, that means we've got a local maximum value because the function is decreasing as we move away from that critical point. If the derivative is positive, that means the function has a local minimum value because the function is increasing as it moves away from that critical point. Similar scenario at a right endpoint. If the derivative is negative, the function decreases to that endpoint, and therefore we have a local min. When the derivative is negative to the left of a right endpoint, and when the derivative is positive to the left of a right endpoint, that means that right endpoint will be a local max value. All right, so those are all the aspects that we need to be concerned with the first derivative test for extrema. When we're at endpoints, we're looking at the behavior of the function as we move away from that endpoint. When we're at non-endpoints, we're looking for sign change in order to determine the type of extreme value that we have. All right. Let's look at example 1. Use the first derivative test to find the x values of any relative extrema of f of x equals x squared minus 9, that quantity to the 3/4 power. So the first thing I'm going to do is go ahead and take the derivative of this. and that gives us 3/4 times the quantity x squared minus 9 to the negative 1/4 times the derivative of the inside. Derivative of x squared minus 9 is 2x. So simplifying this, we end up with 3x over 2 times the quantity x squared minus 9 to the 1/4 power. Okay, so f prime of x is equal to 0. At x equals 0, that's when the numerator is 0. And f prime of x is undefined at x equals plus or minus 3. That's where the denominator is 0. Okay, so we set up our sign chart. And all our critical values are -3, 0, and 3. And we look at what happens. And so I'm going to start with 1. If I put 1 into this derivative, I've got, oh gosh, I'm taking the 4th root of a negative number. And so the function, the derivative doesn't even exist here. All right. In fact, because of the original function being a 4th root, the 3/4 root, since what's inside here is negative, the function does not exist anywhere between -3 and 3. So we can't have a critical point at 0 because the function does not exist there. Now let's try outside these intervals. If I put 4 into my derivative, I get a positive over a positive. If I put -4 into my derivative, I get a negative over a positive. And so there are our situations. All right, so let's look at what's happening here. At -3, the derivative is negative to the left, and it does not exist to the right. Okay, that means that -3 is the location of a right endpoint of the function. So since the derivative is negative, the function is decreasing towards that endpoint, and therefore we have a relative min. There is a relative minima at x equals 3, or pardon me, x equals -3. Since it is a right endpoint, where f prime is negative to the left. Similarly, over here at 3, again, it's an endpoint, but in this case it's a left endpoint. Again, I can state that there is a relative minima because we've got the left endpoint and then the derivative is positive to the right of that. So this is a relative minima at x equals 3 since it is a left endpoint. Where f prime of x is positive. I'm just going to write f prime of x is greater than 0 to the right. And so if we look at Desmos here, we can see a graph of what the original function looks like, and you can verify this situation that we have here. We've got this point right here where it is a right endpoint of an interval, and that's smaller than all the function values around it, and this point here, which it's the left endpoint of an interval, where again it's smaller than all the values around it. All right, let's go on and we'll continue on to the next page. And we see here two important things for us to consider. Important thing number 1, if the function doesn't exist, then x equals a cannot be the location of a critical point. We saw that in the last example where the function didn't exist at x equals 0. And so even though the derivative was equal to 0 there was no critical point because there is no point on the function. Therefore, there can't be a critical point there. And second thing, there's a difference between asking the question, what is the maximum value, and where does the maximum value occur? Where does the maximum value occur? We're talking about an x value. What is the maximum value? We're talking about the y value. Okay, What is the maximum value? That's our y value, or our f of x, or whatever our function is, versus this being an x value. All right, this problem should look familiar. Find all the relative extrema of g of t equals t times the cube root of t squared minus 4. Give the intervals where the function is increasing and decreasing. In the last lesson, we found the derivative of this. Found g prime of t is equal to 5t squared minus 12 over 3 times the quantity t squared minus 4 to the 2/3. And we figured out where the derivative was 0 and where the derivative was undefined, and we drew the sign chart. Save ourselves a little bit of time here. We drew the sign chart. And had this was 0, and this was 0, and this was undefined, and this was undefined, and our derivative was positive, negative, positive. Okay, and so what we're looking for here, and we found the intervals of increasing and decreasing as well in that last lesson. So most of the information that we need for this problem, we've already found. So I'm just going to jet through that quickly. And it's decreasing from negative root 12 over 5 to root 12 over 5. Okay, so as far as the extreme values go, we're looking for sign change in the derivative. And you see right here at x equals negative 12, or t equals negative 12/5, the derivative changes sign from positive to negative. Okay, so that means that I have a relative extrema, I have a relative maxima, and in order to get the value of the relative maxima, I need to take that x value, or pardon me, that t value, and put it into the original function. So I'm going to go ahead and pull up my original function here. Oops. And I'm going to go ahead and substitute negative square root of 12 over 5 in there. And so I've got negative square root of 12 over, come on. Times the cube root of negative, you know what, negative square root of 12 over 5 is just 12 over 5. And we get a value of 1.812. So that's our relative max at x equals negative square root of 12 over 5. That's our relative maximum. And then we have a relative minimum. Here, because of our sign change, we change sign from negative to positive. And so we put positive root 12 over 5 in there. And when we do that, all we've got to do is get rid of this negative sign out here in the front. And so our relative minima is same value, only opposite sign. Relative minima of negative 1.812, and that happens at x equals positive square root of 12 over 5. So this is the relative maximum value, it's a y value. This is the relative minimum value, it's a y value. And these are the x values of the locations where those occur. Okay? All right, we're going to come back for a very short third video to this, or very short second video to this lesson, so that we can finish up the third example next time. I'm going to sign off for this video, and have a great rest of your day. See you next time.